conductivity to data from sensors and beyond. What's more, the digital twin continuously evolves thanks to the flow of data, user experience feedback, and new input, and it's greatly impacting development, production, and operation. In development, a product's behavior can be simulated and tested long before a physical prototype has been built. Siemens utilized the digital twin to develop a world record-setting electric aircraft motor that not only weighs 50 kilograms, but is also 5 times more powerful than comparable electric motors. But it doesn't stop there. The digital twins also unleash the power of 3D printing. In a recent Siemens study for gas mixing systems, insights from the simulation of form and flow behavior were combined with generative algorithms. The result? A truly unique channel shape and configuration, one significantly more efficient than anything previously designed. Even entire factories down to individual machines can be simulated and tested. For instance, robots. It's difficult for them to perform milling tasks because large forces in the manufacturing process lead to inaccurate movements. But with the digital twin, the forces that push the robot away from the milling path can be calculated and compensated in real time, keeping the robot in its path. When it comes to operations, digital twins can compare the sensor data of a real point in real time with the simulation of its point. The availability of the point parallel to operations can be reliably predicted, and sudden disruptions become a thing of the past. But this is just the beginning, and Siemens is already driving the future. Merging digital twins with artificial intelligence allows computers to independently design advanced products. Siemens is realizing this potential right now with Californian startup Hackrod, which aims to build customized sports cars. For development, production, and operation, the digital twin breaks with traditional paradigms and opens up extraordinary possibilities. That's why digital twins are the innovation backbone of the future.
Siemens, ingenuity for life.
We're here in Orlando, Florida at the Siemens Spotlight on Innovation. The concept of a digital twin is becoming increasingly more important in manufacturing. And today we're speaking with Dr. Norbert Gauss of Siemens. He's one of the world's experts on the digital twin concept. Please tell us about your role at Siemens.
My name is Norbert Gauss. I'm with Siemens at Corporate Technology. My responsibility there is all technologies around digitalization and automation.
And what does that encompass?
That encompasses technology areas like the digital twin, like simulation, like cybersecurity, artificial intelligence, IoT, software systems, all technologies that bring together the world of IoT and digitalization.
Dr. Gauss, when we talk about a digital twin, please tell us what that is.
The simple answer is the digital twin is a digital representation of a physical product in all its aspects. Now, the last part of the sentence really is the critical one because it means it covers the whole life cycle of a product. So it describes the product in designing it from a mechanical point of view, describing it from embedded software, from a flow mechanics point of view, and many other aspects, electrical aspects. It also describes, the digital twin also describes how to manufacture the product. It describes how the product behaves during operation and in service and in maintenance. So it covers the whole product life cycle.
Why use a digital twin?
If we have a digital twin that really represents the physical product in the digital world, then we can, where we want, perform tasks in the digital world, allowing us to do things faster. For example, simulation instead of timely and costly prototyping. We can do things much more often until we find the optimal solution. We will spend less resources, both monetary resources, but also manpower.
So the digital twin can be used during all phases of the product development lifecycle, the evaluation, and then the ultimate, even the use of that product?
Yes, in all phases.
It's essentially a simulation then based on the most accurate data that you can possibly pull together.
It's a bit more than a simulation. It's a kind of a simulation of many different models instead of just one. And for the purpose, you then pick the ones you really need for this application.
Tell us about those models.
Typically, the life cycle starts in designing a product or in designing a plant. And this is where you pursue many different avenues. You design products, you build CAD models, you simulate those CAD models, you pick alternatives, you try to optimize, you try to get an idea about the embedded software that has to run on the model, on the physical product. You model this without really implementing and coding it in detail. So you simulate in all the different aspects. So it's models in the CAD area, it's simulation models for software, it's computational flow dynamics, it's simulating electrical circuits. So it's a very broad set of models in the design space. Then in the next phase of let me call it life of a product, when it goes into manufacturing, for example, or installation if it's a larger plant, then you simulate different things. You simulate or you design how to manufacture the product, how well is it built for manufacturability. That allows you already there in the digital space to build a feedback loop, designed for manufacturability by simulating how it's manufactured. Once you have designed the manufacturing, you can engineer it. You can, for example, automatically feed forward this information and automatically generate PLC code, for example. So it's a feed forward loop and a feedback loop you already have in these two phases. During the manufacturing process, then you try to, of course, optimize the manufacturing. So all of a sudden you need a pretty accurate model of the manufacturing site itself, so that you can optimize this part of the life cycle. The next phase of a life cycle then is the longest one, which is operations. So in operations, then you also want to optimally operate the system. You want to, for example, optimize efficiency of a gas turbine or minimize the emissions of a gas turbine. You want to minimize downtimes of a large motor and so on and so forth. Now, during operation, of course, you need a model that is less complex. You cannot afford hours of CPU times if you want to make adaptations and optimizations in real time. So you need to reduce the order of the model, significantly reducing the complexity. At the same time, for the critical components you want to optimize, the model has to be still pretty accurate. So you reduce the order of the complexity of the model so that you can do inline and real-time, kind of real-time simulation to optimize operations. And then there's another important phase, and this is service and maintenance. These are typically data-driven models. So artificial intelligence, when it comes to predictive maintenance, in a way, is nothing else than just another kind of a model, driven and defined by data, but it's a model. So this is the last part of the model in our life cycle. Important is that it's really a combination of a feed-forward loop, where you can automate some of the steps, increasingly more so, and it's also a feedback loop from service into manufacturing, from service into designing the next product generation, from the factory back into design, and so on and so forth.
With so many components, how do you ensure that at each step of the process of the life cycle, that the digital twin is completely accurately representing the physical object itself and the characteristics and the behavior and the implications that flow from that?
As a company, we